All right, everyone, we are back, and now we're going to kind of take a step back. We saw that our last example, we failed on this maximum overshoot design. We didn't hit we didn't hit it, and we weren't even realistically close. But so we're going to do and take a more fundamental approach. And if we have a system, we want to kind of connect it now way back, seems like a long while ago, to this kind of picture of when we have a system of interest, where do our poles lie on this S domain? And then how can we connect essentially the pole location to these time domain specifications? And specifically, how we can leverage these as well as, and then, we know the relationships, sigma and, sigma and omega, how we can leverage these parameters that are related to one another in order to kind of see where our poles have to lie so that we can hit essentially those specifications. So we have essentially a lot of these relationships. So let's go ahead and let's take a big step back. We have our kind of general expression here. And what I'm going to do, I don't know if I want to, I'm not going to. And what we're going to do is we're going to say, all right, here we go. This is our general expression that we're working with. I've created two functions here that show or allow you to, and actually I think the last one is the better one. I don't know why I've redefined it here twice, but there's definitely reasons. We'll redefine our functions. We know what the poles of the system are, and essentially transfer function poles of PS. It's not doing that because it's asking me to do first transfer function model here. So I'm going to just redefine that. It's just I'm putting it in that form so it can recognize that. And so what we get, I have two poles, and we can actually now visualize and look at essentially the poles. So two poles, so we should have, again, we're in the left side of the plane. There's a real component, there's an imaginary component, so we know that our response, as we've kind of seen before, is this exponential decay with some oscillations. Now, what we want to do is we want to kind of create this map or this region of where our poles have to lie depending on our time domain specifications, right? And then see how we can kind of build and predict where they lie, and then how can we shift essentially the pole locations in order to make them fit where we need them to fit. So, let's go back to our goals. So our goals was a settling time of 10.1. We know, and we have our relationships kind of listed out here, if I want to put a bound on settling time and relate that to the pole location, I know that to calculate the settling time, it's just 4.6 over zeta omega n, or sigma. So I can basically set a bound on sigma. So if I have to have a settling time of less than 10.1, I need that sigma to be greater than 0.455. Now, how can we kind of imagine what that's going to look like in terms of our bound? Well, we know that if we increase sigma, right, because our, if we look at our kind of general function, the sigma is just, a value, right? So anything that is greater than sigma, basically pushing us more negative, based on that first specification, which is just the rise time, or the settling time, of 10.1, as long as that value of sigma is greater than, if our pole falls anywhere in this region, this whole thing, anything left of that 0.476, which is 0.455, we're good to go. So, and we see our little poles, which are the positions here, it falls in that region. Now that should make sense because remember, we were fine. We ticked this box, right? Settling time less than 10, we were fine on. The thing that we failed was that maximum overshoot. So we can see, but we're building this kind of framework, right? So we fit in there, we're good to go. Let's go to the second bound. So now we're going to make our region a little bit different. So we need a rise time goal. Rise time goal of less than 0.8. Well, we know our rise time is just 1.8 divided by omega n, and we can set that up. Now, if we go all the way back, omega n, right, So our rise time has to be a specific value. Omega n is basically this radius, right? So we need it to fit within kind of this, basically within this cone, as you're going to, or actually within this kind of radius, as you're going to see in just a second. So let's go back to that. So this is our goal. We're going to use this relationship up here, and omega n has to be greater than 2.25. So let's see how that looks like. So if it's greater than, so basically, because you can kind of see here. So remember, we have to be less than that 0.46, but now our omega n has to be essentially larger than this. So it has to fall, effectively within these bounds. And actually, sorry, we're looking at, this is a different kind of plot here, so ignore this for a second. But essentially, that omega n, right? So it is this angle here, right? So it needs to kind of fall that, like basically a circle or radius greater than that. So we're kind of combining essentially those two regions, right? So it needs to be basically greater than that 2.25 value. So it needs to basically extend beyond that little semicircle, right? So if this is 2.25, like this circle radius, it needs to be greater than that. So it needs to fall, like this is an excluded region. So that's where you kind of see the hole that's being drawn here. Great. Now, what about, now the last thing that we need, we have to relate, and actually we can go through here. And this is, let's go to our last. So we found essentially our radius goal, but what about zeta in our third bound? So we can find what is our, again, we need to hit that 15% overshoot, so 0.15. So we need to solve for zeta. So our zeta, we know it has to be positive, so our zeta bound has to be this. So, and we need essentially this angle to be, again, less than this, so it needs to be essentially greater than this value. So, and we can connect it or create, basically we're using that relationship, remember, and actually we can go back over here. Sorry for going back and forth, but this is why it was important to do that first lecture where my sine of theta is equal to zeta. So we're going to solve for what that angle has to be. So it needs to be greater than that 28 point something degrees. So now what we can do is the other metric, and actually it's kind of, we can kind of go back. We already did this circle, right? So that's not allowed. We also said anywhere to the right of this, that 0.5, that's not allowed, so it needs to be okay here. But now remember, that angle, which here to here, which needs to be greater than that 28 degrees, it has to be basically within, and it goes from here too as well. So anything in here is fine. So that's where we kind of see this, it has to be within this angle. It has to be with basically greater than that semicircle, and it needs to be the left of this. So the only thing that matches, and we can do this with different colors. Let's do that right now. So I'm gonna draw the region that is okay. Actually, I'm gonna get rid of all this stuff so we can kind of visualize this one more time. So first thing that we had was this line right here, and we said anything here is good. Then we said anything basically at that angle, anything in here is good. But then finally, oops, no, I gotta be careful. Oops. Let's do it. Oh no! Please stop. Here. Oh no. Okay, then maybe this. How about? Oh no, but I'm not out. This is not easy. Ugh. There you go. And then just like a little bit here, a little bit here, and then a little bit everything in here. Ugh, but you get what I'm saying. Oh, this is hard to do. I wish it didn't do the automatic, but I like it. And then finally, the last one, let's just do black. It had to be, again, that circle. So basically, everything that is larger than this radii. Actually, you can just kind of wish there was a circle. It kind of like basically extends something like this. So anything that's beyond here works. So that shaded in region, which I'm unelegantly trying to show, that is our design region. And we see that we failed it once we had that condition that related to the angle, which is zeta, which was our maximum overshoot. So I built a cool little function in Mathematica where we can actually calculate that allowable pull region, but we can also even go a bit further. So here, you can kind of see, this is the allowable pull region. And you can see right now, we fail, right? We're outside of that pull region. And if you want to go step by step, we can actually do this and look at when we fail, right? So I can look at this here. So you specify those parameters and I can go step by step. So see, step 1, I'm stable, so I'm okay. The red are my pull functions, so I go, and we've seen this before. Step 1, let's go step 4. Step 2, we're still okay, right to the left. Then it's going to go through our, now overshoot, we failed, right? And then now we can see the final allowable pull region. So this is interesting, right? And I think this is really cool because it's a cool way that we can actually visualize and essentially look at the system and see how it has to basically respond. What does it look like here? Do this here. So let's actually go and what we can do. So this is great, but we still, again, we see that we fail, right? Like it's not working. We're not essentially hitting and putting our poles in a position to be successful. Well, what we have to do, again, we need to overcome that maximum overshoot. So how can we tune our system to position those poles? So we fail with our approach basically to our damping ratio. So let's just focus on tuning that term. Let's not touch omega n and design for zeta. So this is our function, and we know omega n, undamped international frequency is this. We know our damping ratio is this. We need to tune it and not touch this, right? So we don't want to touch the omega n. So what parameter is not in omega n but it's in zeta? This is the thing we need to touch. Well, it's C, right? It's our damping ratio. It makes sense, right? This is where the physical intuition is critical to this control process. If I want to reduce overshoot, I need to increase my damping. That makes sense. Or change my damping ratio, right? So if I want to make sure there's no overshoot, I need to increase that damping ratio. But let's just solve for that mathematically, right? Here we already know our omega n. We've already calculated our zeta before, and it's not sufficient, right? We need it to be greater than, we calculate the value. 0.47 is our cutoff. So if we just solve for this, we can see that as long as we move the new damping ratio to at least greater than 18.8, we're going to put that in the right pole region. And you can see that right here. Now let's show it here. So these are the values that we had previously. This is our zeta min. We can calculate all those good things here. And now we can say, all right, what happens if I were to set my new C to 20? And I can put everything else, the same metrics that we defined previously. Where do we sit in the poles? Perfect, right? We sit in that pole region. If we do 18, you're going to see the red dot move. We're outside. We're not going to be able to hit those metrics anymore. If I go to, 200, let's see what happens. Oh, something interesting happened, right? Now there's bounds and restrictions. So you've got to be careful because now I'm changing essentially what my system's looking like. But you can kind of see here, the poles are shifting. But there's limits. You have to be cautious. And you can see here, I put myself in a position where the system dynamics change completely. This is the other side of controls. You have to be careful. You can't just randomly, and especially I think when people get to PID control, people just change parameters somewhat haphazardly, not thinking about, okay, why is this, or why am I changing this? What could happen? What are the implications? Can I potentially destabilize my system? Can I do something completely different? So But this is the key to time domain specifications. I hope that you use this tool. And then I will see you all in the next video. Thanks. Bye.